Remember that the LME function we're using comes from the NLME package. With this kind of model, you'll usually want to save the model as a stored object and then call the summary function on it. So here I loaded the NLME package, made test model with a random intercept and random slope, and then got the summary of that model. Here is the output that the summary function gives. It is long, so I'll show the rest on the next slide. AIC, BIC, and log likelihood are model fit indices. You'll mostly want to ignore those. They can be useful for comparing nested models in special cases. The first major section is called random effects, and it describes the random terms in the model. In this case, we asked for a random intercept and a random slope of stress, so those are the two random terms. We get a standard deviation for each one, indicating how much variability there was. We also get the correlation between the random slope and the random intercept. This correlation addresses the question, do classrooms with higher test scores also show stronger relationships between stress and test scores? Usually we don't care about this stuff except to make sure that it is reasonable. Nothing is zero and nothing is too extreme. We also get the residual standard deviation here, information about the error variance left over after accounting for the randomness in the intercept and the slope. In other words, the discrepancies from the lines drawn within each classroom. The next major section is called fixed effects, and it is what we usually care the most about. This is where you'll find a table much like the regression tables you're already accustomed to. The overall relationship between stress and test scores is negative, such that 1 unit of stress was associated with around 3.7 percentage points lower test scores within classrooms, and this negative relationship is statistically significant. There are many options for how to conduct this hypothesis test, how to define the p-value, because there are many ways to estimate how many degrees of freedom there are depending on how many observations are in each group, how many groups there are, and how much the observations within groups depend on one another. In this case, the LME function just gave us 19 degrees of freedom as a reasonable default option, and I'm not going to go into detail about all the other options in this video series. Scrolling down to look at the rest of the output, below the table of fixed effects, there is a table of correlations among the fixed effects, showing that the slope of stress is correlated negatively with the intercept, usually not that important, and then the quartiles of residuals just like we'd normally get from the summary output of an ordinary regression model. At the bottom, a nice reminder of the structure of the data that gave rise to this model, 24 total observations in 4 groups, that is, 4 classrooms. Here is what I might actually write in a paper based on a model like that. I fit a linear mixed model with stress predicting test scores within classrooms. This model included a random intercept by classroom and a random slope of stress by classroom. I obtained p-values based on default t-tests in the NLME package for R and the parenthetical citation for that package. Overall, stress was associated with lower test scores, and then the slope, standard error, and p-value from the regression table like usual. This was a lot of buildup for what ends up being basically just one regression slope. There is another major package for linear mixed models. It's called LME4. Most of the time you can use either NLME or LME4. There are some relatively fancy cases where NLME can do something that LME4 can't, and vice versa. So it is useful to know about both of them. LME4 has slightly different syntax. It puts the random part within the main model formula, separated by a plus sign in parentheses, instead of having a separate argument for it. Back to the usual way of doing it in NLME. This code is the same as what I showed a moment ago, except there is one additional argument. na.action equals na.omit. For simplicity, I didn't show this before because my dataset didn't have any missing values. But in many real-world cases, you'll want this argument. As you may recall, the LM function that you're accustomed to by now automatically excludes cases with missing values from the analysis. The LME function is not like that. By default, it simply stops running and gives an error message if it finds any missing values at all. Specifying na.action equals na.omit causes it to automatically exclude cases with missing values, just like LM does. But I've been showing you the classroom example this whole time. What about an example where observations are grouped within participants? In most of my own research, I'm doing something more like the religious prejudice example from earlier. Perhaps each participant evaluates 5 religious groups, reporting their attitude on a scale from negative to positive. If there are 100 participants, then there are 500 observations, 100 for each target group, and observations are clustered by participant. In cases like this, it is common to be unable to include a random slope because I'm interested in explicitly comparing every single target group within my fixed effects. There is only one unique observation per participant for each target group, no room to quantify extra variability. So I've shown example code on the screen where target religion predicts attitude and there is only a random intercept by participant, no random slope. Having only a random intercept is typical for this kind of design. In the next video, I'll switch to looking at an R console and try a very simple example of a repeated measures experiment like this with hypothetical data. One last thing. Sometimes your model won't converge. These linear mixed models are much more complex than the ordinary least squares models we've been focusing on in this class. They have to be fit iteratively. The computer guesses all the important values, then checks how close it is, then makes a better guess and checks again, and so on. That process is not perfect. Sometimes it results in cryptic error messages like this hypothetical example shown on this slide. In those cases, you basically have two options. You can simplify the model by removing some of the random terms, or you can make the computer try harder or try differently to find convergence. I'm not going to go into detail about how to do that in this lesson, but feel free to ask me about it.